In the last few videos, what we talked about was current and how charges on the surface of wires generate electric fields, which allow current to flow. In the next set of videos, we're going to talk a lot about different kinds of circuit elements. We're going to start with talking about resistors, which are able to sort of modify the properties of circuits in ways that we might need. So the way we're going to start this off is actually by going back to talking about the general principles that we have for E&M. So we're going to go back to talking about this idea of a system. And we talked about these principles in some detail at the beginning of the semester, but we're going to remind you about two of them. One is that the change in energy of a system results from external works and thermal exchanges. And the other is that the change in the charge associated with the system is a result of external currents, that is, charge flowing across the boundary. And what we're going to do is we're going to understand exactly how circuits work in the context of these principles. So what we're going to do is start by building a circuit. So we're going to have a battery that is connected to a thick wire that then becomes thinner somewhere. And we're going to analyze what the current looks like in that situation. So we'll start with the new E&M principle, that is that the change in the charge of a system is related to the current, to make sense of this. So we'll start with our steady state assumption, which we introduced a while back. And that steady state assumption suggests that there's going to be no change in the total charge of your system. So this is the idea that no additional charge is sort of flowing across the boundaries. And so as a result, what we have is a situation where the current in all of the branches of this really simple circuit are going to be the same. So what this kind of implies for us is that there's a steady current that at any point along the wire, we expect the current to be exactly the same everywhere. So if I'm looking at, in this case, this is the plus side and this is the minus side. So the electron current goes like this. So that's that electron current. We expect that electron current to be the same everywhere. In particular, we expect it to be the same when we are looking at the thick part of the wire. So let's say that this wire has a thickness, we'll call it A thick. And this part of the wire has a thickness that we'll call A thin to distinguish that they are differently sized. And A thick is greater than A thin. So what we're going to do is we're going to clean up this area here, because what we're going to show is something that tells us about the relationship between the fields that we expect in these two pieces of wire. So in this case, the thick wire has a greater area than the thin wire. But under that steady state assumption, what we're saying is that the electron current in the thick wire is the same as the electron current in the thin wire. That is our steady state assumption. Okay, now we define these quantities in terms of the charge density of the charge carriers. So if these materials are the same, they will have the same charge density n. We described them in terms of the cross-sectional area. So the thick one will have A thick. We described them in terms of the mobility. If they're the same material, they'll have the same mobility. But it might be that their electric fields in those wires are different. And similarly, the other side will have some electron density, will have some thickness to it, which is A thin, and will have some mobility, and it will have some electric field. Now you can see we immediately get a relationship between the electric field that is in the thin wire and the electric field that's in the thick wire, and it's related to those areas, the ratio of those areas. That is specifically that the electric field in the thin wire is equal to the area of the thick wire over the area of the thin wire times the electric field in the thick wire. And so we expect that the electric field in the thin wire to be much greater than the electric field in the thick wire. That is, that there is a larger electric field in this thin resistor to push the electrons through it to achieve the same current throughout the wire. Okay? So this is sort of a general scaling result. So it's a result that helps us understand how the circuit can maintain a constant current. Essentially, we have a big surface charge gradient across this really thin resistor. And so we generate a very large electric field, which pushes really hard on those charges as they move through that wire. And essentially what we also have is a relationship, if we go back to our definition of the average velocity, that the average velocity in the thin wire is much greater than the thick wire. This is just modifying it by the mobility. And so what we find is that the charges will move a lot faster in the resistor, which is kind of odd because we refer to it as a resistor. So it doesn't really resist the motion. What it does is it sort of constrains it and squeezes it so that the speed at which the electrons move through that thin piece of wire is much higher than it is everywhere else. So what we've done in this video is essentially use the very first principle, this principle of the way that the charge changes in a system, to demonstrate that using our steady state assumption, namely that the thick wire and thin wire have the same electron current, that we can get relationships between the electric field, which drives the current, and the velocity which the electrons move with in the different parts of the wire, and show that those are different even though the currents are the same.